Greetings. So this is our one more lecture on computational statistics. Last time we have seen some measures of central tendency, measure of dispersion, and in relation to that, let us move further here. During our different measures of central tendency, we have seen arithmetic mean, geometric mean, median, and mode. And after that, we have realized that studying only measures of central tendency is not going to be enough to understand a given data in a better way. And that is the reason why we further studied different measures of dispersion or measures of variation of the individual observations from their average or mean value. And a given measure of dispersion can be either absolute or a relative, depending on whether it carries certain unit or not. We have seen range, absolute measure, coefficient of range, a relative measure, mean deviation about mean, an absolute measure, variance, absolute measure, standard deviation, an absolute measure, and then coefficient of variation, which is a relative measure. So these are the things. So let us discuss some problems on measures of dispersion. Two or three small problems, and then we are going to switch to the remaining part of unit number 1. Problem is you and your friends have just measured the heights of your dogs in millimeter. So you can see these are the heights. There are 5 dogs of different species. The first one is Rottweiler, and like that. I do not know the names of all this. The heights at the shoulders are 600 millimeters, 470 millimeter, 170 millimeter, 430 millimeter, and 300 millimeter. So we have a data in which there are 5 observations. This is purely a raw data or a primary data. Now what is to be done? Here, find out the arithmetic mean, the variance, and also the standard deviation. So this is the problem. Now we know mean, arithmetic mean, the formula is, actually the notation is x bar. X bar is equal to, for raw data it is 1 upon n summation of xi, running from 1 to n, like that. So these are the 5 observations added together and divided by 5. 394 millimeter is the mean or average height of these 5 puppies. Okay. Now the next thing is that 394 and 10, we have added that line 394, which is a green line. So you can see 3 observations are above that mean value and 2 observations are below. You can understand. Now let us calculate the difference from the mean. So as we know here that the mean is 394, you can understand. So the first observation minus, so there is a difference of 206. From second observation, difference between second observation and the arithmetic mean 76. Third is minus 224, like that, 36 and minus 94. Now to calculate variance, what is variance? Variance is nothing but the arithmetic mean of squares of the deviations of individual observations taken from their average value. And thus variance or sigma square is 206 square plus 76 square plus 224 square plus 36 square plus 94 square. So absolutely difference, you need not specify negative sign. Okay, so this is one formula. So we have used the formula of sigma square variance of x. See, variance of x, original formula has been used, that is summation of xi minus x bar to the power 2, I running from 1 to n divided by n. This original formula has been used. Okay, so we are getting variance as 21,704. Actually, there is exactly simplified form of this also. We have seen that is 1 upon n summation of xi square, I running from 1 to n, minus x bar to the power 2. So you can use the second formula also. That is your choice, which formula to use and when. And finally, anyhow, you are going to get this answer, 21,704. Will be having unit millimeter square. Millimeter square is the unit. Then what will be the standard deviation? Positive square root of variance, and this will be around 147 millimeter. Okay. So as long as there is only one data set, standard deviation is going to be a very standard measure of dispersion. We know this. Okay. So, and the good thing about the standard deviation is that it is useful. Now we can show which heights are within one standard deviation limits from the mean. Now we can see here. So the green line represents the mean, and mean plus sigma and mean minus sigma. The upper line is blue line is mean plus sigma, lower blue line is mean minus sigma, and you see that the first observation is lying above 1 sigma limits, whereas the third observation is lying below 1 sigma limit, and remaining 3 observations are lying within 1 sigma limits. So we can understand that one observation is extreme, whereas another observation is very small, like this. So this is the importance of standard deviation. Using standard deviation, we have a standard way of knowing what is normal and what is extra large and extra small. So this is the thing. So the height of Rottweiler. So we have a puppy of 4 months. So I know Rottweiler very well. Its height is above. Okay, and one is very extra small. So Rottweilers are tall dogs and Dachshunds are a bit short, right? So this is the way. And then I am going to discuss a very important property of change of origin and scale on variance and subsequently on standard deviation also. Let us try to understand the meaning of this. But before that, during the last lecture, I had covered a mode. So I forgot to give an example of the same. See, during every time While discussing every measure of central tendency, I have told the appropriate real situations where a particular measure of central tendency is going to work. And subsequently, I forgot to consider mode. During 11th or 12th in chemistry lab, you must have performed titration experiments. In that, three observations are taken. If all the observations are identical, there is absolutely no problem. Suppose 25, 25, 25. So if you get arithmetic mean or geometric mean or harmonic mean or median or mode, all are going to be exactly equal to 25. No worry. And further, for the same data, any measure of dispersion, range, coefficient of range, mean deviation about mean, variance, standard deviation, or coefficient of variation are all going to be exactly equal to zero. Really ideal data, no worry about that. But suppose out of three observations, two observations are exactly the same and third is slightly different. If you remember, what is the final observation you are considering as? I still remember that. If an observation is appearing twice, then it has maximum frequency and that is considered as mode. So that mode value is taken as the final observation mode. Okay. So that is the usefulness of mode. Now let us move again back to this variance. We know variance and we'll try to understand what is meant by change of origin and change of scale. So I want to tell that if x is a original variable, x is a original variable, the values may be quite complicated and then what is suggested? For some while, you have to change x into y. So for every value of x, find another value of y by change of origin and scale. Now, if we are obtaining a new variable, suppose w, by adding or taking away some constant from every value of x, then we say that we are making change of origin. Suppose w equal to x minus a or x plus b, something like that. A and b are constant. So for every value of x, there will be new value of y. So y is obtained by making change of origin on x. This is the meaning. Suppose we are obtaining z as by multiplying every value of random variable x by a finite non-zero constant, then we say that we are making change of scale. Yes. And if we are doing both the things simultaneously, then we say that we are making change of origin and scale both. Okay. So here I am going to make change of origin and scale. I am going to say y. Y I am going to say y is equal to a into x plus b. Something like that. It really doesn't matter. You can change x to y or y to x. It absolutely doesn't matter at all. Now, my question is, if I know variance of x, what will be variance of y? This is my question. For the same, already we have seen change of origin and scale property in case of arithmetic mean. So that is needed here and we can do it quickly also, no problem. Suppose initially we have been given this distribution as xi and fi over k classes. I is equal to 1 to until k classes. Okay. Now x bar is found by the formula. We know x bar. X bar is 1 upon capital N summation fi into xi. I running from 1 to k. Now the next thing is how to find y bar. Y bar is equal to, definitely the formula is 1 upon n summation fi into I running from 1 to k is equal to 1 upon n summation I from 1 to k fi a times xi plus b is equal to 1 upon n summation fi. A can be taken outside being constant into xi plus 1 upon n summation I from 1 to k fi into b, and that is equal to, you can understand, a times summation fi xi upon capital N is x bar plus summation fi means n upon n is 1, and that is equal to b. So if I know x bar, I can directly tell y bar. Actually, if original is x variable, then we are modifying y and we are obtaining y bar, and from y bar we are obtaining x bar. So I am doing exactly opposite thing, but you can understand. Here y bar is equal to a times x bar plus b. That is as simple as it is. This is change of origin and scale. Actually, you can understand here yi is equal to a into xi plus b. So xi is multiplied by some finite non-zero real number as a, so that is change of scale, and then we are adding or taking away some constant b, then that is change of origin. Here it is both change of origin and scale. Okay. Now we are going to see the effect of change of origin and scale on variance. So here I will have to write the formula of variance of x first. Variance of x. Now we know that variance is denoted by sigma square, but here problem is that we will be discussing variance of x and variance of y also. So variance of x is sigma x whole square. And the formula is 1 upon capital N summation I from 1 to k fi times xi minus x bar to the power 2. Now I want to find variance of y, that is sigma y square, and that is equal to 1 upon n summation of fi times yi minus y bar to the power 2, I running from 1 to k. So this is equal to 1 upon capital N summation I from 1 to k fi times. Now yi, you can see yi is equal to a times xi plus b minus y bar. Y bar is equal to a times x bar plus b to the power 2. So we are doing slowly, and the things will be coming automatically. This is 1 upon n summation I from 1 to k fi times. Inside the square bracket, you can see a into xi minus a into x bar. This is going to be one thing, and plus b minus b cancels. So you are wise enough to understand that this is a times xi minus a times x bar. Okay. So again in the next step, a square will be outside. A square 1 upon n summation I from 1 to k a phi times xi minus x bar to the power 2 is equal to a square into variance of x. So this is beautiful result. And left hand side I will be saying variance of y is equal to x plus b. Such a beautiful result. Variance of x plus b is equal to a square times variance of x. B has totally disappeared. So I will try to explain the meaning of that also. Because of B, there is change of origin. So that means that variance is not affected because of change of origin. What is meant by that? If you find variance of the five numbers 1, 2, 3, 4, 5, that will be same as the variance of another five numbers as 101, 102, 103, 104, 105. Yes, because if I say x as 1, 2, 3, 4, 5, then y will be x plus 100. Because of that change of origin, it really does not hamper value of variance. But definitely there is we are making change of scale that is going to hamper. That means that if I am saying that variance of the five figures 1, 2, 3, 4, and 5 is suppose 100, for example, then variance of 2 times x means 2, 4, 6, 8, and 10 will be 2 square times 100 means it will be 400 like that. Now we know that the positive square root of variance is standard deviation. So let us take positive square root of ax plus b. So standard deviation of ax plus b will be equal to again positive square root of a square. We know that positive square root of a square is a into positive square root of variance of x, that is standard deviation of x. This is another beautiful result. So here also you can say now actually if I want to be perfect, here a can be any finite real number. So I will be saying here absolute value of a. So now it is perfect. So this is all about change of origin and scale property and variance on standard deviation. Now let us try to discuss one example. Calculate the mean, of course, arithmetic mean, and standard deviation for the table giving the age distribution of 550 persons. Now class intervals have been given 3, 4, 5, 6, 7 class intervals are given to us, and corresponding frequency also. Frequencies are 361, 132, 153, 140, 51, and 2. Definitely that must add 2, 542. Okay. Now let us see. So what is suggested here? These are the 7 class intervals mid values. We know mid values are nothing for every class interval. The mid value is found by taking the arithmetic mean of the lower and the upper limits, like that. Okay. So these are the 7 class intervals, and so as number of classes is even, there is no hesitation. If we want to make change of origin and scale, here they are using the word d. Okay, you can use y also. So let me use y. Y is equal to x minus 55 upon 10. Suppose there would have been only six classes. So first have been 25 and the sixth have been 75. So in that case, you can choose either 45 or 55. It really absolutely doesn't matter. And you can see for every value of x, we are getting some unique value of y. X 25 y minus 3, 35 minus 2, 45 minus 1, 55 0, 65 1, 75 2, 85 3, like that. Now let us forget x for a while. So we'll just concentrate y and frequency where to find y bar. So fi into yi is going to be the next column, and after that fi into yi square is going to be the next column. Now we have to do the remaining manipulation using calculator. So I will be using calculator from my mobile, and then only I am going to write here. So meanwhile, okay. Now what is needed to find first? See where to find variance. What is asked? We're asked to find mean. Why? So we'll be finding mean and the standard deviation. Okay. So where to find mean? Here we'll be finding y bar. Y bar is equal to, formula is 1 upon n summation of fi into I running from 1 to n is equal to 1 upon 552, and fi into yi is minus 15. So you can understand. Otherwise, if we would not have used the property of change of origin and scale, then we would have the second last column as fi into xi. So how big would it have been? 25 into 3, 35 into 61, 45 into 132, and 55 into 153. So many big numbers until 4 digit, 5 digit, their addition may be up to 6 digits. So we are minimizing our efforts drastically by making use of the technique of change of origin and scale. Try to understand this. So minus 15 upon 540. So this is minus 15 divided by 542, and that is coming as minus 0.02, big number 7675. So I am saying this much only. If possible, I'll be adding into the memory. I don't, there's not so many provision to keep in the memory. Okay. So here, this is y bar. Now I want to obtain x bar. As we know, yi, as yi is equal to xi minus 55 upon 10. Xi equal to 10 times yi plus 55. And thus, we can say x bar is equal to 10 times y bar plus 55. So that will be minus 0.277 plus 55, and this will be 54.723 if I am correct. So 723. Yes, it is correct. So this is x bar. Okay. Now the next thing is, we were asked to find x bar, so we have found. So you can see minimum observation is 20, maximum is 90, and there are 542 observations. So arithmetic mean is 54.723. Okay. Now the next thing is we have to obtain variance also. So we'll be obtaining variance of y. Variance of y. Again, if you remember, the original formula is 1 upon capital N summation of yi minus y bar to the power 2 I running from 1 to k. But here we have used simplified formula, and the simplified formula is 1 upon capital N summation of fi into y to the power 2 I from 1 to k minus y bar to the power 2. So this is equal to 765 divided by fi into y square. So fi into y square is here 765 divided by capital N number of observations, that is 542 minus y bar means minus 0.0277 to the power 2. So this much. So I have to simplify this, and again using calculator it will be okay 765 divided by 542 minus minus 15 divided by 542 bracket to the power 2 to the power 2, and that is coming as is equal to 1.4107, something like that. This is standard deviation, so variance of 1. And now variance of x will be, you can understand where x is equal to 10 times y plus 55. So variance of x will be 10 square times variance of y, and hence we have to just multiply this by 100. So 141.07 is going to be the variance of x. So we have very quickly found, just we have done the things for y, and then we have used the standard results. We are asked standard deviation is also asked. Okay, so we can obtain standard deviation like this. So there are two ways now. Straight away from variance of y, you can find variance of x and multiply by 10. That can be done, or you can take square root. Now standard deviation of x is equal to positive square root of standard variance of x, 141.07. So you will be getting the answer. Okay, this is multiplied by 100, and then we have to take to the power uh, 0.5. So it is something 11.8772. This is standard deviation. Another way, I have already told you that you obtain standard deviation of y. So here variance of y is in front of us. This is variance of y, 1.41. So standard deviation of y. So what is to be done? You have to take square root of this, where 1.4107 and square root of that means to the power 0.5. So it is coming as 1.18772, and then standard deviation of x will be equal to 10 times standard deviation of y, and that is equal to 11.8772. As such we have found. So this is the way how we can find arithmetic mean then variance and standard deviation in case of grouped or secondary data or frequency distribution. So this is all about measures of dispersion. Okay, we have satisfactorily completed all the measures of dispersion, and now let us come to the last point of unit number one, that is box plots. So box plots is another very smooth technique to identify the outliers. Let us try to understand first the meaning of outliers. Now, if we have been given some particular data which may contain hundreds or even thousands number of observations in it, and definitely some observations are creating nuisance in the same sense that some of the observations are not incompatible with most of the observations in the data. So we say odd man out. So something not suiting can be just picked and sent outside from the group. So something like outliers. An outlier is a value that lies in a data series which is either very small or large and thus affects the overall observation made from the data series. Now, outliers are usually treated as abnormal values that can affect the overall observations due to its very high or low extreme values. So these are really extreme values and unnecessarily creating nuisance towards the interpretation of that data. So what is suggested, just we have to find out outliers, just throw those observations outside the data and you have to carry out a fresh analysis with the remaining observations in the data, so that we will be getting very smooth and the best possible results in regard to the data. And these outliers needs to be discarded, eliminated from the given data series. And for that, we are going to understand the technique of box plot. Now, what is a box plot? Actually, it is a straight line along the horizontal axis. A box lies on on vertical axis or horizontal. So it can be anyway. That is the way of just perception in the range of the sample. So a box and whisker plot is a graph that represents information from a 5-number summary. Those 5 numbers are minimum observation, maximum observation, then first quartile, then second quartile means median, and the third quartile. So these are the 5 important. So this is, we have shown the box plot along the horizontal line. Outliers means what minimum value is allowed. First Q1. Before that, let us try to understand. We have already seen median. Median is the positional average. Median is also called as second quartile or fifth decile or 50th percentile. All things are the same. Now Q1 first quartile. Before Q1, 25% of the total observations are there. Before median, 50% of the total observations are there. Before the third quartile, Q3, 75% of the total observations are there. So Q1 is also same as P25, Q3 is also same as P75. Then the next thing is interquartile range. Interquartile range means Q3 minus Q1 is called as interquartile range. Now minimum allowed in that is obtained by the formula Q1 means first quartile minus 1.5 times interquartile range. So if there is some observation which is so small that it is smaller than Q1 minus 1.5 times interquartile range, so that is to be treated as an outlier and that is to be thrown outside that data. Similarly, here maximum allowed is Q3 plus 1.5 times interquartile range. So this is a box plot in which we have to identify 5 numbers. The first number is minimum Q1 minus 1.5 times interquartile range. Second is Q1 first quartile. Third is median. Fourth is Q3, the third quartile. And the fifth is maximum Q3 plus 1.5 times interquartile range. So this is, now we'll be discussing some problems and then we are going to stop. The problem is, I think, only one problem. Before that, the ends of the box are the lower and upper quartiles. So the box spans the interquartile range. So you can understand the box. So this box starts with Q1 and ends at Q3. And the difference Q3 minus Q1 is nothing but interquartile range. The median is marked by a vertical line inside the box. And the whiskers are the two lines outside the box that extend to highest and lowest observations. Yes. Now, let us consider one example. The following data are the heights of 40 students in a class. So, please try to understand. So, in a row, there are 10 observations. As such, there are 4 rows. So, these are 40 observations, and definitely these observations an ascending order. Okay, so we have to find box plot for this data, and let us try to see whether is there any outlier or not. Construct a box plot and identify the outliers. So here, see friends, we'll be trying to understand finding the different values, minimum value, maximum value, first quartile, median quartile, something like in interquartile range. And for the same, here, let me refer that. Problem here. So let us go back to the summary here. This is these are the formula. Let us find. So the first thing we have to find Q1, median, and Q3. We'll find that, and we'll be discussing about minimum, maximum, like that. Okay, here minimum, maximum will be found later on. But let us concentrate on Q1. But I think median is going to be easier. So here we know already these observations have been sorted. These are 40 observations, and we know that there is no middlemost observation as such, as 40 is an even number. So what we have to consider? We have to consider two middlemost observations. Now 20th observation is 60 and 20th observation is 66 and 21st observation is also 66. We have to take their arithmetic mean. So 66 plus 66 divided by 2, and hence median of this is equal to 66. Median is 66. Now let us try to find quartile number 1. For the same, it is that value below which 25% of the total observations are there. So what we'll do? Divide the entire data into two equal parts. So first 20 observations are with us. And consider the first 20 observation as the entire data and find its median. That will be the first quartile Q1 of the entire data. Now in the first sub data there are 20 observations, so there is no middlemost as such. 10th observation is 64 and 11th observation is 65. So Q1 will be equal to 64 plus 65 divided by 2, and that is equal to 64.5. So I am going to write Q1 as 64.5. Now I have to find Q3, the third quartile. Consider the second half of the data and find median of the second half. That will be ultimately the third quartile of the entire data. So you can see in the second half there are 20 observations, 10th observation is 70, 11th observation is 70, so Q3 equal to 10th observation plus 11th observation divided by 2. Absolutely, it is exactly 70. So third quartile is 70. Now we can find interquartile range. Q3 minus Q1 is equal to 70 minus 64.5, and that will be 5.5. 5.5 is interquartile range. Okay. Now, what is to be done? Minimum value. Here in the formula, I am going back to the minimum value. Minimum is Q1 minus 1.5 times interquartile. So Q1 minus 1.5 times interquartile range. So Q1 is 64.5 minus 1.5 times interquartile range is equal to 5.5, and that is equal to 64.5 minus. Again, we have to do some calculations. One 1.5 into 5.5, it is 8.25. 8.25, and I think $64.5 minus 8.25, that will be equal to 56.25. 56.25 is minimum. Okay, similarly, maximum value will be equal to Q3 plus 1.5 times interquartile range. So this is Q3 is 70 plus 1.5 times 5.5. So this is equal to 70 plus 8.25, and that is equal to 78.25 as such. Now let us see, is there any observation in the data which is smaller than 6.25? No, minimum observation is 59. And is there any observation which is larger than 78.25? No. So this is absolutely our conclusion is. So you can definitely construct a box plot. A box plot can be definitely constructed as such. So to draw a straight line, and accordingly, as per the situation, actually here minimum value is coming as 56.25. This is 56.25. Maximum value is coming as 78.25 and equidistance. So accordingly, we have to go on identifying median 66, 66, median is 66. Actually, some variability. Median is equal to 66. Then Q1 64.5. So 64.5. Q3 70. Q3 70. So as such, we let us see the picture, a minimum and maximum. There is no outlier. Then here we have such presentation, and then this is minimum, this is maximum. Then you can represent your points, then one after the another. So what the points are here, this problem 59, 60, 61, something like that. So 59, 60 something, you can go on denoting small points to represent each value. In the same page it is. So um, before 64.5 there are 10 observations. So 59, 60, 61, 62, 62, 63, 63, then 64, 64, then 65. There are 1, 2, 3, 4, 5, 6, 7, so many 65 observations. So you have to go on presenting like this, and in this way you can complete the box plot. So this is the technique behind the box plot. So with this, we have finished unit number 1, in which we have seen to summarize measures of central tendency, measures of central tendency, in which we have seen arithmetic mean, in which we have to take addition of all the observations, and that is to be divided by total number of observations. So this is the most familiar among all the people, and for finding averages, percentage result, arithmetic mean is going to be useful. Then in geometric mean is nothing but the nth root of the product of all the observations in the data, and that is very much useful in banking calculations, where the amount is compounded annually as per the rate of interest, and in that the amount is increasing in geometric progression. So in that, geometric mean is going to be very useful. The third was harmonic mean. In case of speed and time problems, harmonic mean is going to be useful, and that is nothing but harmonic mean is the reciprocal of the arithmetic mean of reciprocals of all the observations in the data. We have seen median, positional average. In relation to that, we understood three quartiles, 9 deciles, and 99 percentiles, which are very much in connection to each other. And we have seen models. So these are different measures of central tendency. Then while talking about measures of dispersion. So dispersion means variation of individual observation from their average value. So in that we have seen some absolute or relative measures of dispersion, range, coefficient of range, mean deviation about mean, variance, standard deviation, and after that coefficient of variation. So these were the different measures of dispersion. Then there is concept of moment that is not in your syllabus, but the moments. There are three types of moments. Some moments about an arbitrary value, then moments about zero that those are called as raw moments, and the moments about the arithmetic mean which are also called as central moments. There is interrelation among these also. Generally, we are finding moments until the fourth order, and these are very much useful to identify skewness, cortices. Actually, the theme is that understanding only the different measures of central tendency and different measures of dispersion is not going to get the entire information about a given data to us. So we have to we have to uh, study moments also, and from moments we can go for skewness, scortosis also. Skewness, briefly speaking, skewness is departure from symmetry, departure or going away from symmetry. If our data is perfectly symmetric, then we say that skewness is zero. So this is perfectly symmetric data. If the frequency curve is something like that, it is perfectly symmetric, and one speciality of such symmetric data is that arithmetic mean is same as median is same as mode for perfectly symmetric data. Otherwise, we may have some data something like this, or another situation may be like this. So in the second situation, initially observations have less frequency, but as we proceed, the frequency goes on increasing and then decreases immediately. So if we try to speak about this data, then the mode means maximum height and corresponding value will be the mode. Then talking about a median, so 50% observations are here, 50% are here. So this will be somewhere median, and this will be arithmetic mean. So the relation is arithmetic mean is less than median, and median is less than mode. On the contrary, in the third situation, initially there are maximum observations at the initial state, means with minimum values. Uh, Actual values of the variables are small and such frequency is large, and then steadily there are less number of observations at the upper side. So in this case, if we talk about mode, so this will be mode, median will be somewhere here, and arithmetic mean will be somewhere. We can understand that mode is less than median is less than arithmetic mean, and such data is called as positively skewed data. The second is called as negatively skewed data, and the first one is called as perfectly symmetric. So this is really ideal situation. So seldomly we are getting the data which is perfectly symmetric. Otherwise, it may be very close to symmetry. And let me tell you that as the number of observations in a data goes on increasing, then the data is naturally becoming more and more symmetric. And we are going towards the normal distribution. We are going to learn. So this was about skewness, and there is concept of cortices also. But again, beta one equal to mu3 square upon mu2 cube is the formula, and coefficient of skewness gamma 1 is equal to root of beta 1, and hence it is mu3 upon mu2 to the power mu3 to the power mu3 square upon mu2 mu3 square upon mu2 cube, huh? Beta 1 mu3 square upon mu2 cube, and then beta gamma 1 will be mu3 upon mu2 to the power 3 by 2. And we can understand that if mu3, the third central moment, is negative, then it will be negatively skewed as second. If it is positive, it will be positively skewed, and if mu3 is 0, then it will be perfectly symmetric. Because in numerator mu2 is second central moment, that is nothing but variance. I have already told you. The same thing, and this is about skewness, and there is concept of kurtosis also. So kurtosis is a measure of pickedness or flatness. Measure of pickedness or flatness of the data. If we observe that our data is more or less symmetric, then we can have a situation like this. So this may be one possibility. Another possibility may be like this, and the third possibility it is flat. These are three different data. Different possibilities are there, and kurtosis for that we have to find beta 2. Beta 2 is equal to mu4 upon mu2 to the power 2, and gamma 2 is equal to beta 2 minus 3. If gamma 2 is equal to 0, it is called as mesocortic. It is normal. This is normal. This is mesocortic. If gamma 2 is greater than 0, it is leptocortic. And gamma 2 is less than 0, it is platycortic. Now, which from the remaining is going to be leptocortic and platycortic, we can understand. If mu2 is variance, if variance, it's flat one, so there will be maximum value of variance, and b2 will be smaller. So that is example of this is platycortic. And if beta mu2 means variance is see, this is heighted. This heighted is will be having minimum value of variance, and hence beta 2 will be bigger value. So gamma 2 will be greater than definitely greater than 0, and it will be leptocortic. So this is the way we have to remember. As such, we have finished unit number 1. Let us see, you will try to finish unit number 2 as early as possible. So let me know the screenshots. I have taken screenshots, so let us stop here.